Our last speaker, Paul McNamara, is responsible for overseeing the technical management and delivery of the Williams Advanced Engineering's expanding range of projects in the automotive, motorsport, energy, defence and civil aerospace sectors. He will now speak on the challenges of vehicle electrification.
Good morning, everybody. Very interesting couple of talks. I'm going to give you a bit more of an engineering perspective. So I'm an engineer. I've been an engineer all my career, working with cars, internal combustion engines. I've been at Williams about 3 years. Before that, I worked out in China for 4 years, working for Shanghai Automotive on putting cars into production in China. So I'm very much going to talk about what's this all about, how do we make these products happen, what's the difficulties with it. Williams, founded in 1977, 40 years old last year. The thing that's got us into electrification is Formula One with the kinetic energy recovery systems that were introduced back in 2009. At that time we had a Renault engine. The teams were allowed to do their own KERS, kinetic energy recovery, which meant essentially a battery, an electric motor and a control system that went into the car. 2014, the regulations changed. That had to come from the engine supplier themselves. We shifted to Mercedes. All of that came from Mercedes. We'd built up a large test facility, engineering facilities, etc., to handle all that. Formula E. Out of that, we got involved in Formula E. We supply all the batteries to the Formula E series. It's an electric race car series. We manufacture them on site at Grove, and we also operate the Jaguar team. If you ever watch that series, that's run by Williams out of, again, the site at Grove. So that's why we're into electrification. Why are we into the broader industry? Williams is essentially a completely independent team. So its revenue comes from 3 places. One, winnings, depending on your place in the previous season. Second, the income from sponsors, stickers on side of cars. Third, what we can do with advanced engineering, as we call it, to leverage the capabilities and facilities we have to earn money from that. So we are working with the automotive, military, healthcare sectors to use tech from Formula One. And electrification is one of the biggest areas for us. Right, that's Williams. So some old history, and I think this is really some great insights for us. So back in the 1880s, the car of the mass market was an electric car. It was not a petrol car. Up until 1911, the largest selling cars in the world were electric cars. And the reasons for that were simple. There was no petrol infrastructure, whereas in the cities there was already electric developed infrastructure. If you traveled between cities, there were perfectly good railroads that did that for you, so that the cars of the day were mainly inter-urban transport. Range was therefore not a problem. The situation started to change as infrastructure started to change. Roads between the cities became more viable, petrol became available. Henry Ford came along and started to produce a very low cost, practical, reasonable internal combustion engine cars. There were also difficulties with the initial technology back then because the internal combustion engines were noisy, smelly, difficult to start. The electric ones overcame all of that. So across the 1911 to 1920 period, it faded out. Internal combustion engines dominated. Electric cars disappeared into the background. We're now sort of coming forward again. We now have a second age of electric cars. For me, the 2 key players in this game that have made this happen are Nissan first. What they did was they're the first people to put a lithium-ion battery into a car, making it a sort of viable weight working. And then Tesla, who came along first with their first car to make electric cars a bit more sexy, a bit more accessible. And I think one of the previous speakers was talking, the initial efforts from most of the OEMs were not attractive cars. Tesla made it attractive, put cars out of there. That forced everybody else within the OEMs to bounce in and start doing something. And we had the situation that's been discussed in various talks. So what goes into an electric car? I'm going to talk about all these bits. And And I've used an exploded view of a Formula E car just for fun. But essentially what we've got is we've got a motor. So that's an electric motor. We've got an inverter. That's a little bit of power electronics that allows us to create a rotating field from a DC current into the motor. We have the battery that stores the energy, and we have a gearbox that sits on the back of the motor and transfers the torque to the wheel. So those in essence are the components that we're talking about in this move to electrification that are different to what we have in the current cars of today. Right, so a little bit of a discussion back to basics about gasoline versus electricity. So we all talk about power. It's kilowatts or horsepower. It's the rate of doing work, how quickly we can work, how fast the car's going to go, how much power we've got. Energy is the storage of that power. So in a gasoline tank, I store energy. It's in there. In a battery, I store energy. We talk about that as kilowatt hours. You buy energy from electricity, it's a kilowatt hour. That's the sort of unit of the future. Specific energy is how much power can I deliver per kilogram, how much energy storage, how many kilowatt hours can I store per kilogram. Right, so let's have a look at gasoline and lithium ion. So in gasoline, we store 13,000 watt hours per kilogram. In the sort of current lithium ion technology, we store 230. So gasoline is more efficient than a battery at storing energy by a factor of 50. So for the engineers, big challenge number one to deal with how do we manage that in the context of a car. Next problem is that the price of gasoline is around 11 pence per kilowatt hour, looking at that, whereas the price of electricity about 17 pence per kilowatt hour, so more expensive. So again, how's this all going to work? Why is it that there's electric cars out there and you hear these sort of fundamentals? And you do see these sort of fundamentals around. So why does an electric car work? Given those sort of things stacked against it, why does it work? So the first thing is gasoline engines or diesel engines, let's say, are actually horridly inefficient. Yeah, so the best you can get out of them is around about 40% in practice for what you're doing. So whilst you have that gasoline, you can't get at that energy that's stored. You can get at it in your central heating boiler at home because you can make that about 90% efficient, so you're just getting out straight heat. But if you want work out of it, you can only get about 40%. So a load's going in the coolant and a load's going out the exhaust as hot air. So you've immediately got a factor of 2 at least there. I mean, most electric motors are around 95% efficient, so you can very easily get out the full energy from your battery. The other thing is electric motors are nice and light compared to the internal combustion engines and all their systems that we've had over the last 100 years or so, because not only does the engine go, the coolant radiator on the front goes, the exhaust system goes, moving fuel around the car goes, all of that goes, and that saves you a lot of weight because you're still left with this factor of 20 or so against you in terms of battery to petrol storage. So the two things that are making this revolution work from a sort of engineering perspective is electric motors are very light, internal combustion engines are very inefficient and relatively heavy. And we can get the numbers working much better for us. But you are still left with a challenge. The bottom line is you're trying to store energy in a much less efficient way in terms of weight. So this is a picture of a car. The red is shaded in all the bits that are part of the internal combustion engine powertrain and the electric propulsion system. The big difference is that that's a V8 engine, that's the torque tube, that's the petrol tank. All of this is battery. What you can see a little bit there is motor. So we've had to substitute all that volume with battery. All of that blue battery. The energy storage is that little bit there, the fuel tank. So that's the sort of trend you're getting into. You're packaging battery in cars instead of all this internal combustion engine and all sorts of other stuff. A battery, what's it built up of? So the industry talks about cells, modules, and packs. So the cells generally come from China or Korea, and they are essentially becoming commoditized. So I have some 18650 cells here, picture on the left, and I have a pouch cell, which is the other sort of tech, which is, so these are lithium ion cells that get produced in factories. These are the sort of building blocks which OEMs and others work on. They get formed into a module, which is a way of engineering these together into a manageable block, typically somewhere between 50 and 100 of these, probably 10 to 20 of those in a module. And then they get formed up into a pack. So you've got sort of industrial processes dealing with the cell, industrial processes performing it into modules, and then putting it into a pack, which is very specific to the car. How does a lithium ion cell work? It's essentially got a lithium-based solvent in it, and it's moving lithium ions between the anode and the cathode. And a lot of the technology, as one of the previous people said, is actually in the coatings on the anodes and cathodes. People talk about NMC, the previous speaker talked about different ratios as that's changing. I've got a slide on it, but a lot of the tech is about chemical composition, which is coating on thin sheets of aluminium or copper, which are forming the anodes and the cathodes. Lithium ion cell was invented and first demonstrated in Oxford University. So now it's made all around the world. The only people making them in anger in the UK are Nissan up in Sunderland and a company right up in the north of Scotland called AGM. They're a small prototype supplier of cells, and the big players of China and Korea and Japan in making them through our British invention. That's my plug for more investment and industrialisation here. Cell formats, I've probably covered most of this. The cylindrical cell is the Tesla choice, so a lot of people know that from Tesla. People talk about 18650s. That means that it's 18 millimeters in diameter and 65 millimeters long. I'm not quite sure where the zero came from the back. At the end of that, there is a new move to a slightly bigger cell that will probably start to dominate, so-called 21700, which means it's 21 millimeter diameter and 70 millimeters long. So those tend to be good for quite high power type densities. You can cool them more easily. The pouches, which is the other one I'm holding here, you can store more energy, a bit difficult to get quite so much power out of it. And prismatic in the middle offers a sort of compromise by the two. It's essentially, in terms of the industrial process, a sort of squashed cylindrical cell, so you still get the metal casing on it. When you're engineering a pack, you've got a choice, and Tesla are really interesting on this. So typically those small ones in a car, you'll have somewhere between 6,000 and 9,000 of those built up into your battery. So it's quite an exercise in putting it together. Now the interesting is the more of those you can put in, the more your energy storage goes up. So you've got a weight and a package problem with it, but it also helps you with the amount of power you can deliver. So the manufacturers, Tesla here, offering a choice of energy storages. So 60s, this is a few years back, they've actually dropped the 60, 75, but you can currently buy it, I think, in 85 and 100 thing. And this is going to become the new 1.6 litre, 2 litre, 2.4 litre car of the future. So if you go down the pub, you want to talk about how cool your car is, how much storage have I got, I think is going to become the topic of the future. And I think the public will start to sort of grab this as a number. The interesting thing is the more storage you put in, generally the more power you can get out of it. So Tesla talked about a Roadster with 1,000 horsepower, I think, recently, but they also had a 600-mile range, because the only way of engineering a car with that much power was to give it a colossal range. The sort of two ended up coming together, and that's sort of one of the features of trying to do electric cars. A little bit of what's going on sort of at the top end of the market. So typically somewhere around 90 kilowatt hours and 100 up to 100, with a power typically around 200, 300 kilowatts up to 400 horsepower then is where it's going at the premium end. And this is, I'm talking about electric vehicles, not hybrid plug-in hybrids. And most of those batteries are going under the floor as the most pragmatic way of storing, somehow fitting it into the car. So you've got the Tesla, the Chevy Bolt, and the Jaguar I-Pace just being launched at the moment with sort of quite similar schemes. So cell energy density is a key sort of battleground. The more we can store in a cell in terms of kilowatt hours per kilogram, the better the cars get, the more efficient the whole thing becomes. So the technology to do that is a sort of fight going on, Samsung, LG, Sony, and others with it. Right now, we are at around about 250 watt hours per kilogram. That will probably head to about 350 as a peak, and then the technology runs out of steam. Beyond then, we need some new innovations. So lithium sulfur is a new chemistry. New is not the right word. A chemistry that's been around that offers certain advantages. Particularly, it stores a higher amount of kilowatt hours per kilogram, but at a higher volume. But for the aerospace industry, that is of interest. And we're doing a couple of projects with aerospace guys thinking about lithium sulfur batteries on that. So I think a push for technology to increase that kilowatt hours per kilogram. My opening comments, it's all about trying to reduce the mass in the car to store the energy. Cathodes, so nickel, magnesium, cobalt oxide, NMC so-called, and NCA are the two popular things. And as a previous speaker said, there's different formulations within that's tending to make nickel more dominant within that sector as people try to remove the slightly more expensive chemistries. Probably a little bit too much detail, but there's a roadmap out to 2023 involving silicon and NMC, and also trying to get into ceramic coated separators that should keep improving the standard of batteries and therefore the competitiveness of electric cars across the next decade or so. Just for interest, for those people that have a sort of mining interest in these things. So for a cell, I've sort of tried to break out at an elemental level what goes into that. So if you've got a 70 kilowatt hour pack going into a Jaguar I-Pace or something like that, you've got 8 kilograms of elemental lithium, 55 kilos of copper, 30 kilos of nickel, 10 kilograms cobalt, 10 kilograms manganese, sort of thing. You have some sense of it. So copper is quite interesting because the reason you end up with so much copper in the thing is because the battery is trying to get the powers people want at the voltages you can do. So you're somewhere between 400 volts and 800 volts. You've got to move a lot of current to get the power. If you're moving a lot of current, then you need a lot of copper conductors to move that. So you'll see in the battery and the cars of the future a greater use of copper than has gone on before. Typical costs, and these are at a cell level. So the numbers quoted earlier were at a pack level. Remember, it's talked cell, module, pack. So cost per kilowatt hour at the moment for an 18650, as published by Tesla, around about $150 per kilowatt hour, something like that. And a similar for a pouch. This is what GM says the best we can get in the market. Bear in mind we're a small player. It is more like $190 or so to get hold of a pouch like that. And then you've got all the costs of converting that into a module, converting it into a pack that drives up the cost per kilowatt hour. So the electronics in a electric vehicle are very substantive. So you've got to both manage your high voltage energy to the inverters and motors, which I say are typically between 400 and 800 volts is the standard at the moment. The more performance cars are at 800, the more regular cars at 400. In order to run the rest of your car ancillaries, you still need 12 volts, so you end up with a DC-DC converter to take your 400 volt battery back down to 12. You also either are going in directly to your battery versus via some sort of controller, or you've got another DC-DC converter to deal with your plug-in point to your battery if you've not set. Most of the network is ChargeModular can confirm at 400 volts at the moment, the charging system. So if you've got an 800 volt pack in there, you'll need another DC-DC converter to get it back up to 800. So a lot of power electronics in there as well. You need an onboard charger usually, because people do want to plug into the wall. So most OEMs are still giving you can plug in this little 12 volt, this little 240 volt thing that goes in. So usually an onboard charger for that as well. And all of that's got to come together. So people involved in power electronics manufacture will benefit from all of this. Electric machines. So that they're another key new component that are in there. So induction motors essentially mean that you just have copper windings on cast iron or steel. Permanent magnet motors means that one of the stator or the rotor is a permanent magnet involving the sort of rare earth elements. In general, the permanent magnet synchronous motor is lighter weight and a bit more efficient. The induction motor is a bit cheaper, a little bit less efficient, and it doesn't need any sort of funny rare earth elements at all. And the market is quite split between that. If there is a trend at the moment, people are heading a bit more towards the permanent magnet motors. But I think my own guess, and it is nothing other than a guess, that as industrialization speeds up and we get more and more volume, I think the ease of producing induction motors for the mass market will probably mean that the number of induction motors will start to dominate. Detailed picture of a permanent magnet motor. Again, gives some sort of sense of where's all the materials in that, for those interested in that. So steel at 35%, copper 20%, so another source of copper in the car, and then a number of rare earth elements. Induction motor, steel, a lot more copper at 39%. So inverters, this is the other power electronic component. So in taking a DC energy source and converting it into a motor, you have to have a bit of electronics in there, which is changing a steady flow of current into an alternating current in 3 phases. It's also what sort of governs the power going out of the motor and the speed from the motor. And it looks like a printed circuit board in a box, essentially, when you look at it. Again, copper 25%, aluminium 40%, plastics, and generally some switches, which are the sort of the raw material of how these things work, which are essentially chips. Yeah. All right, charging infrastructure. Some general comments, not as detailed as the presentation we've just had from ChargeMaster. Generally, charging stations, I'm talking about the public ones, limited to 50 kilowatts. There's a bit of a push in the industry, and again, as a product guy, I'm much more interested in how can I produce a product that sort of looks and feels like a gasoline car today, so I can charge it quickly, I can have 200 or 300 miles range. I agree with all the comments that's gone on before, as the market may well change, but if you're sat in the OEM space, I'm not an OEM, that's how I work with, your mindset is provide something that sort of does what cars do today. So 50 kilowatts, that will allow for most journeys, you to charge within 20 minutes or so, something like that, and get 50 kilowatts. Well, if you get 50 kilowatts in an hour, you can get 20 kilowatts in 20 minutes or so. That allows you to press on with your journey, having stopped at a motorway station. But I think the trend's going to be for the capability of the power of the charging stations to increase. We can get more and more power into the batteries quickly, and that will mainly become an infrastructure requirement. I agree with the previous speakers from all our discussion with the National Grid. They're confident they can provide the electricity. There is no problem there. There's a great website, if anybody hasn't looked at it, called Grid Watch, and it instantaneously tells you where all our electricity is coming from at any given moment. And there always seems to be plenty of capacity there. The coal-fired power stations are very rarely on. If you look at that, it's mainly from wind, nuclear, and gas. The difficulty is often seen to be local networks, as mentioned there, is can we get the power to all the houses and the local charging stations, not the ability to generate electricity in the first place. And the faster, more powerful we want these chargers. But there is a thinking, again, I agree with the previous speakers, that what will end up happening is a lot of these will go into existing petrol station forecourts in the end. The model will continue, you'll get multi-fuel there. this is a European perspective on the deployment of stations. So that's 3.5 million stations across Europe by 2020. So yeah, a European view that the number of charging points is escalating very rapidly. Wireless charging. So from, again, an engineer's perspective, the question is, will the infrastructure develop enough that's needed? Because I've got to put an extra pad on the bottom of the car that looks something like this, yeah, that you drive over, and inductively the two things interconnect. So it's a bit of extra mass from the pad itself, and it's also an extra load of charging electronics to regulate what that's doing and put it in, and a third means of charging effectively in terms of what I've got there. So whether that really takes off or not, to be honest, very difficult to guess. There isn't a massive drive, I can say, to put that sort of stuff on the bottom of cars as standard at the moment. But you could imagine a world where that's there. All the car parking slots have one just under the floor. Then it would work. A summary of sort of observations from the engineering side of it. So I would say transport electrification being driven by the improved capability of the vehicles. You can go out there and buy cars now that essentially do what you want them to do. They are practical and commercially viable. But there's a load of other factors driving it: Dieselgate, urbanizations, and the availability of renewable electricity sources. Because it's very important that our electricity is renewably generated, or the whole thing doesn't work. You know, that's for sure, sort of thing. Yeah, because if you're generating electricity in the first place with a sort of 50% efficiency from the fuel you're using, you're better off just putting it in the cars straight away, sort of thing. So it is important that works, or else the CO2 benefit is not there. There is a pollution benefit, but not a CO2 benefit unless you're generating electricity renewable. The engineering challenge moves from power creation in an internal combustion engine to energy storage. So the whole industry is moving much more towards energy storage. How can we store energy more effectively? Cost reduction driven by high adoption rates will make the cost competitive or better. Said in the previous presentation, we agree. The interaction of the vehicle with the charging infrastructure is a key part of the proposition and service. So you know, the OEMs can only survive and push it whilst there's charging infrastructure there, which should both be at home and out in the public world. And the numbers I have in my head is actually around 55% of the population don't have access to easy off-road home parking. So, you know, what is there in the public domain, I think, is going to be important. But as somebody said, I mean, we've still got a captive market of 40% or so who can charge at home. So we're going to see 10 years of growth anyway. I think hybrid vehicles will play a major role in the transition. So plug-in hybrids, I think that's going to be a lot more acceptable to a lot of the population. So I think those sort of cars, the Mitsubishi Outlander is still one of the highest selling electric cars around, and I'm sure that will carry on. But in the long term, hybrids will be a transitional technology, and we'll all be in full electric vehicles 20 years from now or so. Real-world electric vehicle range is going to put an emphasis on aerodynamic performance and efficiency at higher speeds. So one of the things that's actually gone on with the auto industry for the last 30 or 40 years is that exterior design is driven by aesthetics, not by aerodynamics. But now that we are much more concerned with how we save energy, the aerodynamics will become important, and that side of the industry will be important. Good, and that's it from me.
Thank you, Paul.
Thank you.
And thank you, everyone, for being here. Thank you particularly to our speakers. That has been an extremely insightful morning, as I'm sure you will all agree. A couple of points that I have certainly picked out from this is, one, it's the ease of use of the cars, and the habits of consumers now will be a major driver perhaps. Issues of safety, machine learning, what's going to happen with jobs and education amongst the people, and are we perhaps 20 years behind where we should be, given the whole carb issue that came out. The links between battery electric vehicles, fuel cell electric vehicles, what's the future for the national grid? Are we going to have private sector companies coming back in? And what about the second-hand market of cars? These are just some of the things that I have taken away, and it leads to a huge debate in the future. Thank you very much.